my research has to do with how we can incorporate electric vehicles into the power grid. So we are solving sequential decision-making problems. And we're using reinforcement learning for that. Why? We're going to see soon. Let's start with an introduction. Why is this problem important? And I promise that GNNs will come to be very useful soon. So we know very well that the number of electric vehicles increases a lot, exponentially, we could say, because of the transition goals we have. We want to have carbon-free emissions. We want to have electric vehicles. We don't want to have normal combustion engines. But what does this mean for the electricity grid, having all these thousands of electric vehicles? It means that we have very huge energy demand peaks. As you can see, this is for public chargers, like the charger we can see on the streets. There are some times of the day that the load can be very high if we don't control it. For example, in the morning when we go to the work or when we return home after a hard day of work. So we need to do something. Let's see an example here with just 5 electric vehicles. We see that one electric vehicle is there, it can charge maximum power, a second, a third, etc. We see that if we just don't control the charging part of this, in the end we have some overloading, we have some constraints that are being violated, technical constraints like transformer limits. What's the solution for that? We can just shift the loads in time because we know that electric vehicles will stay connected for long. Maybe they are connected at night and then they stay for the whole night there until the morning. So we have the property to shift the loads in time. However, this is not easy when we don't know how long the V is connected. Maybe we have some other communication problems. We don't know the state of charge because of some limitation of the protocols. So we have a sequential decision-making problem and we have a lot of uncertainty. Imagine we have an electric vehicle, we connect to a charger, we don't say how long we stay there, right? We'll just, at some point, we just leave. So we let the charge point operator to try to define how our charging schedule will look like in order for when we leave, we have maximum power, maximum energy. Here, I would like to show you just an idea of how a problem like this looks like in practice. So we have 3 different types of objects, actually 4. We have the charge point operator, who is responsible of deciding how fast its electric vehicle charges. Okay, please now. So yes, we have a CPO who is responsible to charge all electric vehicles. He trades energy in the energy market, so for every time he has a specific energy he can use. So his job is to maximize his profit and try to split the energy evenly to all electric vehicles that come and go. So we see electric vehicles come and go. And as you can see, we already have a graph structure here. And another property which is very useful here is that electric vehicles come and go, so the state is dynamic. How is this problem usually solved in practice? Using classical mathematical optimization is not very efficient because as the number of electric vehicles increases, then we don't scale very well. We know this, so we should go to machine learning methods and see how this can work for us. What does this mean? Reinforcement learning, very useful for solving this type of problems. But let's see how reinforcement learning looks like, how it's a usual loop. We have an environment, which means this is a charger, the electric vehicles, the transformer limits, etc. We have the policy, which means what actions we're taking. In this case, this is the CPO, charge point operator. And we take an action, given a specific state. And of course, when taking an action, we take a new state, and we also get a reward. The reward can be anything. In this case, it can be cost, it can be deviation from the power set point. And the action is how much the Vs are going to charge. And in reinforcement learning, usually we have 2 separate networks. We have the policy, the actual network, which takes us into all the state. And also we have the value function or critic or action value function, which takes us into the state and sometimes also the action. So we have these 2 networks in reinforcement learning. So in this problem we saw before, the state can look something like this. We have some information about general information, the time set, the set point, prices. Then we have information about every electric vehicle disconnected. It's like the this can be anything. Energy already charged, how long it is connected there. Now, what happens if we have a few thousands of electric vehicles or a few thousand of chargers, because we solve this from a perspective of the CPO? Then we just have a very long vector, right? And we have a second problem there, second limitation. At a lot of points, in some cases around 60% of the times, the charger is not occupied, which means we have to put something there. Using classic reinforcement learning with multi-lane perceptrons requires a fixed size input. So we need to put something there. We need to put zeros. Putting a lot of zeros is not very effective, as we know. So let's see how we can solve this with graph neural networks. So this is how we are reinterpreting the EV charging problem. Like I mentioned earlier, we have 4 different types of objects. We have electric vehicles with green, charging stations with gray, transformers, charge point operator, and this is how a specific snapshot of the environment can look like. Of course, every type of object has different features. Electric vehicles might have features about how much energy they charge, how long they stay there. Then we have some constraints from the chargers. We have some other local constraints from the transformer level, and then we have some aggregated constraints. So we see that we have a lot of different objects with different features. One other thing I want to note here is that we have some chargers that are not, that don't have any connected electric vehicles. What can we do there? Well, in practice, these nodes do not contribute to the decision-making process, because even if the end action for these nodes is, I don't know, charge at maximum power, then nothing happens because there's no electric vehicle there. So what we thought is, why don't we prune these nodes so we can use so we can have a more compact state representation. So this is what we did. So in every step we have a graph. This graph can change, so we have a dynamic state. And we need to find a way of how we can take a dynamic state to produce an action in the end, and also combine with the state to produce a value. To give you an idea of what the value is just one value that rates how good the current state and action combination is. So let's see how we can tackle such a dynamic state for solving this reinforcement learning problem. First step is the feature extractor, where we have node-specific embedders. For example, for electric vehicles, we have a specific embedder that transfers the node features to a higher dimension that is common for all nodes. So having these node-specific embedders, we transfer all the nodes to the same dimension. So we have a homogeneous graph now. What does this mean? Now we can just apply classic GSM operations. In the case of the actor network, I remember, takes us into the state and has to produce reactions for every electric vehicle connected. What do we do here? Okay, graph formation, graph GSS, followed by ReLU for nonlinearity, and then we go to the last layer. The last layer has to be for continuous space, when the action takes values from 0 to 1, it can be just one feature. So we end up with a graph like here, where each node has one feature, and this feature represents the action. Something to note here, the action is only useful for electric vehicle nodes, right? It doesn't mean something if the charger has an action 1, doesn't do anything. So what we do is we map the actions from the EV nodes to the action vector in the end. So by doing this, we have a neural network that is invariant to the number of electric vehicles currently existing on the graph. As you can see, we can have one electric vehicle, 1,000, and the neural network will still present an output. Another thing that is very interesting with this architecture is that in the last layer, we can have multiple features, like 3 different features, where if we use a softmax, then we can assume that if the first feature is higher, then we charge at maximum power. If the second is higher, then we don't charge at all. But if the third is higher, then we charge at half power. So this way is also applicable for multi-discrete state spaces. For multi-discrete action spaces. All right, we talked about the actor. Let's talk about the critic architecture. In the critic architecture, we need to combine the state and the action. So what we do is we take the state from our switch extractor and then also the output of the actor network and just concatenate it. So we get this very nice new feature vector for every node. Then again, we just do some classic graph operations. And in the end, because we need to only produce one value, one graph, one value for the whole state and action, we take a mean pooling, and then we have a feature vector that is invariant again to the number of nodes. And we have an MLP in the end, and then in the final step, we just get one value that again is invariant to the number of nodes, which is very useful. So let's see some results. What did we do? We try to solve the problem with classic reinforcement learning algorithms. You might know them. If you don't, it's okay. These are the more common for continuous action spaces. Then we have 4 problem settings, one with just 25 chargers, which is quite simple. And then we have some very complex ones, like with 1,000 charging points. This means that we have 1,000 decision variables. This is very, very complex. And the metric we're comparing is the optimality gap. And what does this mean? We mean that we compare the best reward achieved with reinforcement learning minus the oracle reward, the reward that we assume we know everything. Of course, this reward is not very practical. I mean, we cannot achieve it in practice because we don't know the future, but it gives us the maximum experimental value. So the lower the reward, the better. The lower the optimality gap, the better. And we can see that in a very complex case, we can achieve, for the same algorithm like soft actor critic, can achieve up to, like, from more than 500 optimality gap, we can go down to 200, which is very, very big increase if you see. Let's see some more results. Also one thing more. So what we did, we also compared how reinforcement learning would look like if we just use feature extractor. So we had a network where, again, we had this graph, we had the feature extractor, and then we just followed it by main pooling and MLP. So this is like an in-between of not using a full GNN architecture. And we see that, yeah, using a feature extractor GNN, it improves the results, but yeah, it's not enough. Using an end-to-end GNN is also better. And let's see now why this works. There are 2 things I would like to point out. The first one is sample efficiency. As you remember, our state vector no longer has a lot of zeros. It doesn't have zeros at all. So what we learned here is that by using our approach with GNN, we learn much faster. So in the same time, we can achieve better rewards. So this is how we see that it's more sample efficient. Another thing, we have a lot of symmetries in the network. If you remember from before, maybe it's better to show it here. This is a special type of graphic. This is a tree. So we have a lot of branches that are similar. Maybe in this case, where one transformer is connected to one charger and one electric vehicle is symmetrical to another branch that might have the same characteristics. So at this time, we're very sample efficient. Another thing that's very important in reinforcement learning is taking invalid actions. So with classic reinforcement learning, the outputs can be like 11 kilowatts for this car, 11 for this, and 7 for this. And you say, okay, there is no EV here, no electric vehicle. Why do we have an action? Well, we don't have any constraint in classic reinforcement learning with MLPs that we cannot take this action. We always have to produce an action for things. But with GNN, we don't produce an action at all because we don't have this node in the network. So this is also another reason we have increased sample efficiency. Let's see some generalization results very quickly. So we tested in different domains with increased variation. So we trained on the original and then tested on the other variations. And we see that, again, using EVGNN, our approach, end-to-end GNN for reinforcement learning, give us the best generalization. And again, we assume this is because of the symmetries in the graph and the sample efficiency, etc. And one last thing, we tested it also in multi-discrete action spaces for the same problems. It works very well. We have very big improvement gaps. And also it can work for other type of charging problems like multi-objective problems. So we see we also have very good performance there. So if I want to keep two things for you from this presentation is that using GNNs is very useful for dynamic states. It can handle them very well. And that this method is not only applicable for electric vehicle charging, it can be applied to any problem with dynamic state, like vehicle routing or portfolio optimization. So yeah, I think that's all.